Okay, I think we're live now. So I will go ahead and introduce our next speaker. So I'm Katie Schumann. I'm an assistant professor at the University of Tennessee. And I'm very excited to introduce our first invited speaker of this year's workshop, Priya Panda. Priya is an assistant professor at Yale University, and she leads the Intelligent Computing Lab there. And we're very excited to hear her talk today. So, Priya, I'll hand it over to you.
Thank you so much, Katie. And first of all, a big thanks to the organizers for inviting me to this exciting workshop. And today I'll be giving you an overview of some of our works that we have done in the co-design space for enabling scalable spike-based machine intelligence. And before I move on, I have to acknowledge my students who have done the crux of the work, and I get this opportunity to present their work. So as we all know today, deep neural networks, they are achieving massive feats in terms of doing a lot of tasks from recognition to natural language processing. But the question still remains is at what cost? So here I'm just giving you an example, a deep neural network which is doing simple object detection on backend GPU. It expends on the order of a couple of 100 watts of power. On the other hand, the human brain, we perform impressive feats, not just recognition, movement, control, planning, decision making, all of that, but with a very small power budget of 20 watts. And whatever little we know of the brain, we know that it is the spike driven computation and communication between neurons and synapses in the brain, as well as the fact that the brain has this 3D structure where neurons and synapses are co-located. And probably these two things are what allows the brain to do these impressive feats with such a low power budget. So in the field of neuromorphic computing in general, what we are trying to do is from an algorithmic end, in order to harness some of these spike driven computations and communications, we are trying to use spiking neural networks in order to integrate these cues such that we can not only harness energy efficiency for intelligent tasks, but also get some interesting improved learning capability because of these temporal computations. And on the other end, on the hardware end, we are going beyond the standard CMOS architecture space. We are looking into more emerging non-volatile memory-based analog computing architectures that can help us further accelerate these computations and come up with more efficient spike-based machine intelligence. So before I go forward, I just want to kind of, I'm sure all the entire community here will be aware of it, but just want to highlight some of the fundamental differences between an SNN and an ANN. And mainly, as you can see here, from a structure perspective, SNNs can have the same structure, a fully connected, a convolutional structure. However, the inputs and the outputs to an SNN are, of course, binary spikes, which come over a period of time. And given that we are processing these binary inputs over time, we need to definitely have a very different neuronal functionality that can take into account some of these temporal correlations. And in SNNs today, at least the works that I will be talking about, the neuronal model that we use is this leaky integrate fire neuronal model, wherein you have this membrane potential shown in blue that has this integrate and leak behavior in the presence or absence of spikes. And whenever the membrane potential crosses a certain threshold, that is an indication of the generation of an output spike. And this output spike is then communicated to the rest of the network. So this is all good. We have a good neuronal model, we have a structure, but the problem is this thresholding functionality. As we all know that whenever there is a thresholding functionality, the activation function becomes discontinuous or non-differentiable. So you cannot use these standard gradient descent techniques. We have to modify the gradient descent techniques so that you can come up with gradient, so that you can actually train these spiking neural networks from scratch. So there's a lot of work that has happened over the past decade in terms of how do you efficiently train deep spiking neural networks and kind of scale them up to some realistic tasks. And to that effect, there is a good amount of work that exists in the standard STDP learning field, or spike time independent plasticity learning. But turns out that while this is a very good unsupervised local learning rule, scaling up models towards more realistic large scale, not only recognition but detection tasks, turns out to be a problem. So they are very much limited in terms of the kind of accuracy, as well as you cannot really have very large networks trained using STDP. Similarly, then, people moved on to the conversion technique, which is very much widely used today. There's a good amount of work coming up in a lot of interesting conferences. And here, the good thing about conversion is that it takes advantage of standard ANN training. So you take a pre-trained ANN model and transfer the statistics of that pre-trained ANN model into an SNN. But turns out, in order to have a lossless conversion between an ANN and an SNN, you need to show the input for longer time steps. So the latency during the conversion process has to be long enough for you to have this good accuracy, and that latency will automatically result in higher energy also at the end. So today, like at least in our lab, what we have been focusing on is training from scratch. So essentially thinking about what type of backpropagation or backpropagation variants can you come up with, such that you can leverage the time statistics in the input time statistics of these LIF neurons very well, and can come up with a spiking neural network that not only has lower latency but can be scaled up to large scale models such that you can do more realistic tasks. And we want to leverage this backpropagation through time learning rules in order to not only get efficiency, higher accuracy, but also some interesting robustness benefits. So one of the first things that we did in our lab that allowed us to do some kind of scalable from scratch training is this learning rule called batch norm through time. Now, what is this batch norm through time? It's basically trying to modulate your batch norm layer that exists in every ANN that you train today. But instead of having a constant learnable parameter, given that your input to an SNN comes over a period of time, so it made sense for us that this learnable parameter attached with the batch norm layer should also vary or should also change over a period of time. So it turns out, the implementation of it is pretty standard. You attach this BNTT layer before your convolutional operations coming into an LIF neuron. And what I want to just give you more insights rather than the implementation details, and maybe if you have any questions, I can take them in the Q&A. But interestingly enough, one of the first things we try to do is that once you take this trained model, we wanted to see what kind of spike activity do you see with a BNTT trained model as compared to previous conversion models or your standard surrogate gradient descent trained models. And we found out that previous models like conversion and surrogate BP, when you look at the spike rate across different layers, there is this kind of, initially there is not a lot of spike activity, and after a period of time, it sort of has this saturating activity. So all layers spike at a saturated rate after a period of time. Whereas in case of a BNTT trained model, you have this kind of a Gaussian train wherein the spike activity rises and then falls down, right? So we wanted to understand this further, and it turns out that this kind of a rise and fall is actually associated with the learned BNTT parameter. So what we see is this gamma parameter that is learned over a period of time. There is this time shift of the maximum gamma. So here in this color chart, I'm showing you what is the gamma learned for different layers of the spiking neural network. And you find that the first layer has the maximum gamma at the first time step, second layer at a later time step, and so on and so forth. So and if you know that if gamma is high, means that your spiking neuron will have a higher chance of spiking. So the rate of activity will be higher. So what we see is that there is this interesting temporal propagation of spike information as we go deeper. And gamma is actually, the learnable gamma parameter is able to capture this kind of a temporal propagation. And if you think about it, it makes intuitive sense, right? Early layers should spike first and then the later layer should spike. So with the help of BNTT, we were able to achieve this kind of intuitive behavior. So coming back, given that we have these learnable internal parameters that capture the temporal propagation of spikes, it turns out that as soon as we attached BNTT, we were able to now train SNNs, much deeper SNNs, going beyond the 5 layers, 9 layers, etc. And we were able to train your standard 16-layered or 20-layered SNNs from scratch with very low latency of 20 to 30 time steps. And again, the latency component was able to be reduced because now, given that we have this learnable gamma, it was able to capture the temporal statistics in the input very well, as a result of which it was able to give us high accuracy at low latency. And here I'm just showing you an example result of a tiny ImageNet model trained using BNTT, and we find that the BNTT model was able to get good accuracy as compared to your conversion model at almost 1/10 of the latency. So given that we were able to deploy BNTT, we went ahead and started to think of, can we apply BNTT to beyond recognition, like, your standard image classification tasks. So certain things that we did was applying BNTT for image segmentation. Now that is even a more difficult task, because now you have to go ahead and, like, classify each and every pixel in your input to figure out, which regions of interest are present in the input. And we actually looked at, like, a DVS data set in this case, and we found out that we got really state of the art performance as compared to, your previous SNN methods. And we also not only did that, we also found out that especially when we look at DVS data sets or these neuromorphic data sets which have very sparse information coming over a period of time, you can actually come up with some interesting data augmentation schemes that only are very specifically fine-tuned for DVS data and not really amenable with your RGB sensor data. And again, using a BNTT like learning rule, we with the right kind of augmentation schemes, we were again able to get really state-of-the-art performance and get almost 30% improvement over previous works on these DVS data sets. So accuracy, yes, we were able to achieve using this from scratch training rule. But the question was, are we also able to get energy efficiency? And turns out, yes, because of the fact that now BNTT captures this interesting temporal statistics, we found out, and I'm just showing you the spike rate here of BNTT model as compared to your conversion and your standard surrogate gradient descent trained model. And we found out that the overall spike rate of the overall spike activity of these networks also reduced when you're using learning rule that captures the temporal statistics very well. So we found that BNTT reduces the spike rate by more than 50x and 10x. And of course, if you have a reduced spike activity, that means there is overall higher activation sparsity. And with the right kind of hardware, you can take advantage of that sparsity in order to give you energy efficiency. Now, an interesting side effect that we found using this BNTT trained model was we were even more adversarially robust as compared to other models. Now, this is something that a lot of other authors or other researchers have also shown, that SNNs turn out to be more adversarially robust than ANNs. As you can see here, that as I increase the strength of the attack, of the adversarial attack, the surrogate gradient trained SNN is more robust as compared to an ANN. But what we find is that a BNTT trained SNN is even more resilient. Like, there is hardly any change in accuracy in this kind of medium range of attacks. And if you go beyond this medium range and start attacking in a more stronger manner, even the accuracy drop that we observed was less than 5%. So it turns out that, there is a good amount of advantages to leverage as soon as you start thinking of how do you interpret time statistics very well. So given that we were able to capture BNTT, we then thought about, as I said, we not only went for beyond image classification scenarios, but we wanted to really deploy SNNs for more diverse learning scenarios. As I'm showing you here, we went ahead and came up with some interesting interpretability tool to understand why are SNNs more robust. We also applied SNNs in privacy preserving distributed learning scenarios. And this is something very much amenable with SNNs. We have been talking about SNNs for more edge computing. So it turns out that, if you apply SNNs to federated learning or privacy preserving distributed learning scenarios, they do give you some interesting advantages. So I'm just going to talk about the federated learning part right now and show you some of the interesting results we get. And just what is the framework of federated learning? The federated learning is basically a cloud system talking to multiple devices, and these devices, instead of sharing their data with the cloud, what they share is their model parameters, right? So each of these individual devices is being trained on their own data sets, and instead of sharing the data, because you don't want to share data between to maintain the privacy of the data set, so you instead share the model parameters, right? So you're just communicating the gradients of the model parameters, and there is this back and forth that happens between the cloud and these devices that are being individually trained. And this is a pretty standard federated learning setup. What we did was that, because we know already that we are motivated, SNNs do have a low power alternative, and they can be, since we can now train them from scratch using this kind of learning rules, what we thought was, like, why don't we train an SNN in a federated learning paradigm, wherein this on-device local training of the SNN was done using BNTT. And of course, we were using the standard federated averaging in order to do this communication of gradients and aggregation of gradients at the server. Now, I want to sort of talk to you about like some of the interesting results that we found. So what we found is that SNNs turned out that if you see the graph here, I'm just showing you the accuracy. You see that when you have a low client configuration, that means when you have just 1 or 5 or 10 clients communicating with the server, then SNN's accuracy is lower as compared to an ANN's accuracy. But as soon as the number of clients go beyond 100, right, as you see here, the SNN's accuracy starts becoming much better by almost 30 to 40% as compared to that of an ANN. And turns out that this federated SNN training is actually robust to all aspects of federated learning, which means that if you have heterogeneity in terms of data, you have some stragglers, that means some of the devices when they're communicating to the cloud are being dropped off, or maybe you may have some noise during the communication process. And all of that, SNNs are much more resilient as compared to ANNs. So this again tells us that at the end of the day, there is this SNNs not only have a low power alternative, but they can do more scalable learning, especially in the distributed paradigm. And of course, like, we have to still measure the energy efficiency and see that actually when we are doing this online training and inference alongside with these multiple devices, are we actually getting an energy efficiency? And turns out this is an analytical energy estimation we did on 45 nanometer CMOS process. And we found out that an ANN as compared to an SNN consumes more than 5x energy for doing this kind of a distributed federated inference in these kind of scale devices. So moving on, now we wanted to think about like, yes, we are able to reduce the sparsity in case of an SNN, but is spike rate reduction just is that the only goal, or can we further sparsify the SNN in order to get even more improvements? So what we wanted to then further look into was, can we have some interesting weight and temporal sparsity? And to that effect, what we looked at is pruning. Like, pruning is a very widely used technique today, and we all have heard about this lottery ticket hypothesis, which allows us to get very interesting subnetworks from dense initializations. And we essentially investigated lottery ticket hypothesis for SNN pruning techniques. And in terms of lottery ticket hypothesis, what we found out is that in case of an SNN, we not only can prune the weight dimension, which is the space dimension, but we can also prune the time dimension. That means when we are searching for these sparse subnetworks inside these dense network, we not only need to search the network with longer time steps, but we can search the network with shorter time steps. So these winning tickets can be drawn from a network trained with a smaller number of time steps. And after you have found out this sparse subnetwork, you can of course train it and fine tune it with the number of time steps that is initially assigned to you. So this was again another thing that, there is 2 degrees of freedom in terms of pruning that you can apply to SNNs and get even better results. So turns out that, when we did this early time, we call this method early time ticket, and this work was presented 2 weeks ago in ECCV. And we found out that, we were really able to reduce the search time of these sparse subnetwork finding by almost 40 to 50%, depending upon the type of initial lottery ticket hypothesis method you're using. And again, we were able to maintain a very good accuracy while observing a sparsity of almost 97 to 98% in terms of weights. So the key takeaway from here is that when you're thinking about pruning, you don't only think about spatial pruning, but also you can think about temporal pruning when you're looking into spiking neural networks. So far, I have sort of kind of hopefully talked to you about like the fact that, from scratch training techniques that use temporal statistics can definitely make a difference in widening the use of SNNs for diverse applications. But the question is better training optimization the only way to enable spike-based machine intelligence? Well, the question is, let's try and look at the full picture. So if you look at the fundamental differences between an SNN and ANN that I have already highlighted, there is an LIF versus a ReLU a structural difference. There is a temporal information processing versus a static input processing functional difference. But despite of these differences, we always, till now, so far, whatever results I have shown, I have always used ANN architectures like VGGs or the ResNets. But the question is, because there is this kind of a difference, that might actually result in a suboptimal solution. So the question was, can we find more SNN specific architectures? And what we did in our recent work was we applied a NAS algorithm to search for some suitable architectures that SNNs might prefer. So we applied this NAS algorithm. So one of the first things that we wanted to think of was which NAS algorithm will be suitable for SNNs, given that SNNs have a significantly slower training process. So we cannot apply, your standard gradient descent train based NAS algorithms. We came up with this zero-shot NAS training inspired from one of these ICML 2021 works. And again, in terms of the search space architecture that we were looking at, we not only were trying to allow the SNN to search for the type of convolutional kernel, but also the type of connection in terms of skip, no connection. And in addition to in addition to forward connections, we also started looking for backward connections. And turns out, and I'm just highlighting the results here, that SNNs actually prefer backward connections and get even better accuracy as compared to an SNN that is restricted to search only for forward connections. And when I say backward connection, what does that mean? It means that the computation of this neuron is influenced by the computation of this neuron, and so the computation of this neuron at a current time step is influenced by the computation of this neuron from a previous time step. So there is this past from later layers trying to influence the current in the early layers. And this sort of interesting temporal dynamic that is being captured by the backward connections is something that SNNs are preferring, and we can come up with even better architecture search techniques. And one other thing I also want to talk about is the fact that these searched architectures were transferable across data sets. That means a CIFAR 10 trained architecture was transferable to a CIFAR 100 or a tiny ImageNet. And as I said, given that we were using this kind of a zero-shot training algorithm, we were able to find these best architectures at very less search time of less than 2 GPU hours. And the GPUs I'm talking about are very simple RTX GPUs. So moving on, I have talked to you about the algorithmic perspective, and in the last 5-6 minutes, I just want to give you a brief idea about the hardware perspective to just really give you some thoughts around, are SNNs truly efficient when implemented on hardware? So when we started thinking about the hardware perspective, first thing we wanted to talk about was can we actually benchmark some of our algorithms? And turns out when we started looking at benchmarking tools for SNNs, they were missing. There were a lot of benchmarking tools available for ANNs in both the crossbar space as well as the systolic array space, but benchmarking tool for SNNs were missing. And so to that effect, in our group, we developed these two different types of benchmarking accelerators. One was called SpikeSim, which is a crossbar-based accelerator, and one was called SATA, which is a systolic array-based accelerator for SNN training, whereas SpikeSim was for SNN inference. And I'm not going into the details of SATA. It is a standard systolic array design, which has functionality to do LIF neuron, do the weight fetches, etc. But I just want to highlight some of the interesting details about this training accelerator we found out in terms of results. We found out that when we are not considering the sparsity at all between an ANN and an SNN, of course, our SNN consumes more energy as compared to an ANN. But when we do consider sparsity, that means the sparsity of ReLU neuron is considered, sparsity of SNN neuron is also considered, or spiking neuron is also considered. It turns out even after considering sparsity, the training energy of SNN remains higher than ANN. So the reason was that, first of all, we found out that, time steps, it turns out that does play an important role. If you have very large time steps, you really cannot win over an ANN in terms of computations. And that is because every time you keep on fetching these weights, these membrane potentials back and forth between the DRAM to the memory array or to the PE array, you are losing out a lot in terms of energy consumption. So this expensive memory access does prohibit SNN training. The other thing that we also found out, which was an interesting finding, was that there is a lot of potential for you to increase the sparsity of gradients. So specifically, there is this gradient of membrane potential that will play a big role in terms of training. And turns out by controlling the sparsity of this membrane potential, you can go to a regime where SNNs will have lower energy as compared to an ANN. So in this case, we found that, if your sparsity in this membrane potential is more than 88%, then SNN starts to win over ANNs. So basically, this encourages, possible direction of new algorithm design for SNNs with more sparsity in these gradients. And we want to use further in the future, we want to use SATA as a platform or baseline to measure the energy efficiency again of new algorithms for SNN. With SpikeSim, similarly, again, it's a hardware evaluation tool for in-memory computing. Not going into the details because I want to keep some time for Q&A, but I just want to highlight some main results. When we try to benchmark these SNNs on these in-memory computing crossbar-based accelerators, it turns out one thing we found out was that there is a huge area of overhead that SNNs have because of the LIF-IF neuronal module. And why is that so? Because in SNNs, we have to store all the membrane potentials over a period of time such that we can do the processing of the spiking neuron. And this is absolutely absent in a case of an ANN, because in an ANN, a ReLU is simple comparator functionality. So, the thing was that what can we do? So what we found out was by just doing some simple topological modifications, wherein we started reducing the depth of these first layers or second layers in the spiking neural network, we were able to get some interesting area minimizations, and that further led to interesting energy and latency minimizations, as you can see. So, this benchmarking further allowed us to think about what new algorithm designs we can do or what new architecture designs we can do. And again, as I said, here, when I compared an SNN to an ANN on this kind of a benchmarking tool, we found out, and here I'm doing a comparison between a 4-bit weight SNN with 1-bit spike activation and a 4-bit weight, 4-bit activation ANN. We found out that SNNs with time steps less than 4 can only achieve lower latency and energy at ISO accuracy as compared to that of an ANN. Anytime we go beyond 4, the energy latency of that SNN starts getting higher and higher as compared to an ANN. So again, we need to have SNN algorithms with low time step count. And finally, this is an interesting work again. When we are looking into these crossbars or any of these hardware tools, we need to bring in variability. And turns out whenever you bring in variability, the fact that you're doing multi-time step computation, anytime you have variability in the hardware, because of multi-time step computation, you will have a compounded effect. And that compounded effect will lead to a huge accuracy drop on the hardware. So as you can see here, even though my SNN was on the software baseline, it was 99% accurate. At the end of the day, when you put it on the hardware baseline, the hardware level accuracy is going to drop down all the way to 10% because of, again, these multi-time step computations. So it turns out you have to come up with some kind of, a post-training adaptation or post-training conservation techniques in order to help you manage these variabilities once you have mapped these SNNs on hardware. And I'm not going to go again, not going into the details. This work was presented at ISLPD this year, which won the best paper award. But interestingly enough, variabilities also play an important role when it comes to multi-time step computations. So to conclude, what I want to showcase here is that energy efficiency is, of course, a primary advantage we get with SNNs. But it still remains to be seen that whether the current hardware that we are developing, are they amenable with the multiple time step computations and the redundancies that happens because of these multiple time step computations alongside SNNs. And true hardware implementation is very necessary for us to understand and truly reap the benefits of these event-driven SNNs and even architect new algorithms. And of course, algorithm hardware co-design will be necessary for next generation neural computing. So with that, I would like to thank you all for your attention and open the floor to some questions.
Thank you, Priya. That was great talk. A lot of questions in the so far. Please feel free to continue entering questions as we go through. We have plenty of time for a Q&A. So I'll go ahead and start with the questions from the audience. Is there a bioplausible explanation for how BNTT might be implemented?
Oh, that's a good question. Yes. So if you think about, we never actually went from a bioplausible side. We were really thinking about, given that batch norm was such a popular technique that allowed to or enabled accelerated training in the ANN space, we thought that it should have a similar kind of effect if used in the correct way in the SNN space. Now, interestingly enough, as I showed you that when we actually trained the model using BNTT, we found that there is this kind of interesting temporal propagation of spikes, right? That means the first layer spike first, then die down, and then the later layers take those spikes and then spike later. So I think from a bioplausible side, maybe what I think the batch norm parameters are capturing in the input distribution is this kind of, that there is this layer-wise time propagation of information, which probably even in our visual cortex might be happening, right? Like, first your V1 and V2 will spike, and then they will carry forward that information to the later layers. And also one thing you see in that BNTT model, which I never had a time to talk about, is that after a while, like even though you train the network, even if you give it like an entire time horizon of, let's say, 25 time steps, right? It turns out that the network figures out that, I may not need fully 25 time steps. The BNTT layer, it turns out that, after 20th time step or so, all the layers have zero activity. So even the network tries to figure out during this learning procedure as to, even though I give it long time steps, it tries to figure out what is the actual activity do I need in order to do my classification, and then the network just sort of stops spiking altogether. And as a result of that, in that work, in BNTT work, we actually proposed this temporal early exit. That means after the BNTT has died down, we don't need to really expend any more effort in the later time steps. So I don't know if that answered the question, but I felt like this temporal propagation of spike information is something that automatically the learning optimization rule captures, which is a very interesting bioplausible technique. Yeah.
So continuing on the theme of the BNTT, so BN can be absorbed in the preceding convolutional layer at inference time. The questioner says, I suspect that this is not true for BNTT because the coefficients change with time. Do you see that as a problem for implementation on hardware?
So that's a good question. Actually, yes. So it's not a problem for hardware because after we, let's say, train the model, so we store the gamma 1. Let's say if your time steps is 25, then during the training, I learn the gamma for every time step, right? Gamma 1, gamma 2, gamma 3. So after the training has been done, whatever gamma I have learned for these 25 time steps, gamma 1, gamma 2, I kind of store it in an array. So literally, like, on a hardware perspective, let's say, when we were looking at SpikeSim or even SATA with BNTT, we literally had like a batch norm storage, like a little SRAM that you can push inside the PE, wherein during inference, every time a new gamma is being fetched inside each processing engine. So basically, as you would have done with an ANN, where after training you store the gamma values per layer, here you not only store the gamma values per layer but also per time step. So per layer, per time step. So there will be a little bit of an overhead in terms of storage memory of batch norm parameters. But again, the time steps that we are talking about is like 30 to 25, so it's not really much as compared to what you would have stored.
So another question from the audience: will BNTT work with recurrent networks as well, or just feed forward?
That's a very good question. So yes, I think the recurrent models that you are talking about can be different, right? Like, would BNTT work with something like a transformer attention like model versus an LSTM like model? So we actually try to apply BNTT on a transformer model. Not a recurrent model because of the fact that and there is this theory going on that spiking neurons are inherently recurrent in nature, right? Because they have this membrane potential being stored over time and computed over time. So they have some inherent recurrence. So we wanted to take advantage of that and see if we can build better attention models. Now that is work under progress. We are hitting some problems there, and that is because if you see these attention models that we have in transformers, they don't have a lot of activation layers. They have more of these matrix multiplication layers. So there, a batch norm can really derail some of these the query, key, value, the attention map capturing. I have not yet applied BNTT on LSTM or your gated recurrent units kind of models. So that would be something could be interesting to see how that performs. Yeah.
So we have a couple questions about the federated learning results that you talked about. I think you touched a little bit on the energy usage later in the talk, but But a question from Dan, is the federated learning process feasible for spiking neural networks? The forward pass for SNNs is usually relatively low power, but the backward pass, as you presented, is very expensive.
Yeah. So when I did federated learning, it was fully with SNNs trained from scratch. So like literally local on-device training was done using BNTT, and then we were doing federated aggregation of these spike-based gradients, all of that. We were able to, as I showed, we were able to scale it up to 200, 300 devices talking to the server, right? It was slow. It will be much slower as compared to an ANN, because again, we are doing multi-time step computations. So that energy, when I showed that SNNs were 5x more energy efficient as compared to ANNs, that was all inference estimation, not the training estimation. What I think right now we are looking at in the federated learning space is combining these the sparse models that we found using these lottery ticket hypothesis, where you can do temporal and spatial pruning and apply them to distributed learning space. So that's where probably we can still get some interesting advantages. Having said that, yes, training is something we really need to figure out as to as I showed later on, with that SATA benchmarking, we found that until unless you sparsify the gradients or you are in the limited time step regime, you will never be able to get an SNN which is lower in terms of training cost as compared to an ANN, right? And that extends to on-device training, all of that. So we really need to think of bringing in more sparsity, not only in terms of weights, in terms of gradients, and further minimizing the time step count. So what I showed in the federated learning results, that was all done with SNNs, but the energy results that I estimated was only during inference. But yes, we need to take some of these techniques that we have done and we need to apply it in the federated scenario. So hopefully, Dan, that answers the question.
So another question, and I'm actually going to jump in also after this with a question from me, selfishly as the organizer. This is about the NAS approaches that you applied. Could you elucidate a little bit further which architectures you were performing NAS over? The results you showed were for COM-nets with COM backward connections or fully connected. So what sort of architectures were you actually looking at for the NAS implementations?
So we took when we were searching for these when we were doing the neural architecture search, we took a cell-based architecture, right? So each cell will have, so when I showed that circle, it's basically a cell which can have this array of operation choices, right? A skip connection, a 1x1, a 3x3, or 5x5, and all of that. So it will choose. It never searches for a fully connected, in the search space, design search space, that was our search space inside each cell. So it's sort of like every cell somehow is a convolution operation, which could be skip connected to the next cell. And it could choose multiple convolution layers in some way, right? It's not like it will always prefer a 1x1. It can prefer 1x1 and 3x3 together. So sort of multiple convolutional layer architecture in some way. So that was our architecture. Now you can tell me, so we initialized this kind of a cell-based supernet, and we tried to sample subnets. And as I said, when we were trying to figure out how do you sample the best subnet, we use this Hamming distance based technique, because we did not want to come up with a darts or proxyless NAS like technique where they not only train the weights, but they also train the architecture parameters. So there was no gradient based search done. We literally use some statistical techniques like Hamming distance measure, wherein the spike, so we initialize the supernet, and the spike activity of that initialized supernet, by measuring the spike activity and doing some kind of statistical Hamming distance analysis, we were able to find that which subnets that we sample from the supernets might have a better accuracy. And again, that this statistical measurement, it was theoretically proven by that ICML 2021 work, and we took it and we modified it for the spiking neural network. So literally there was no gradient based search done. It was a fully statistical search. So in a sampling way, you just figure out which network may have better accuracy, and then you train that network to convergence and figure out what's the best accuracy model. So hopefully that answers the question. So we are looking into convolutional architectures and this kind of a gradient-less search.
Okay, so this is where I'm selfishly going to jump in with my question. So you, with the NAS and with the really nice tools you presented for energy analysis, Have you considered doing a multi-objective NAS where you can target high accuracy but also very low energy usage?
Yes, yes, Katie, that's a good question. That's really work under progress right now. We are targeting a DAC paper in 2 weeks, and literally this is like co-optimization, as
Right.
you're saying, because that was as you said, it is pretty much the next thing to do. That now that we have a benchmarking tool, we will append it with the NAS search tool there, and we'll have this kind of a network architecture, hardware search optimization all together. Yes.
Excellent. Excited to see that. Okay, so another question from the audience. In the energy efficiency experiments, you compare ANN and SNN energy consumption on static data. So you're turning the static data into temporal data for SNNs, and if when you're doing that, what sort of technique are you using?
So we like most of the yes here most of the time I have been using either direct coding or rate coding. When I say rate coding, it means that each image is converted into each pixel in the image is converted into a spike train, wherein the pixel intensity is proportional to the frequency of the spike train. That is rate coding. But turns out that sometimes when you go very deep with these 16 layered, 19 layered architectures, it's always better to feed the image as it is, which is RGB image. And at the first layer, so after you go through the first conv operation, you will have a LIF unit, and that LIF unit will anyways produce spikes. And so there are two types of coding, which is today very popular. One is direct and rate, and we look at both of them. Temporal coding, wherein you restrict one spike per neuron across all time steps. That is something we have not yet explored. It is something that could further give you more efficiency, but there are certain problems when you want to scale it up. So we are trying to figure that out. But yes, at this point of time, it's only direct coding and rate coding that we have looked into.
Great. Okay, so this is a very popular question from the audience. For anyone interested in running SNNs on hardware, which platform do you recommend to use, and how can we gain access to that?
Yes, so I have shown here all codes available on my lab's GitHub website. So SpikeSim and SATA are available there. We are, because of the fact that SATA was accepted very recently, we are trying to kind of come up with the entire tool flow. So all of it with SpikeSim and SATA both are available, and we are still updating that platform as and when students are coming up with questions around how to do this, how to do that. But both of these platforms are available in terms of benchmarking tools. Some of you who may have access to Loihi can of course do that. We are also trying to get some energy comparisons done between, let's say, SpikeSim and SATA and Loihi, given there is a different type of an architecture space there. But at least firsthand you can take some of these tools, SATA and SpikeSim, and develop your algorithms on top of it.
Okay, and a last question from the audience. This is your last chance, audience members, to get in Q&A before we move on to the next talk. What was the motivation to link federated learning with spiking neural networks?
Yeah, so it was basically motivated from the fact that at the end of the day, federated learning, if you think about it, at the end of the day, the inference is done on my device itself. So we need to, during inference, have an extremely low power model that is being used in order to do the inference. So, and we wanted to do federated learning because it kind of captures this idea about privacy preserving distributed learning, where you don't share data and all. So from a training perspective, of course, federated learning with SNNs will be inefficient, and unless you kind of import those techniques of sparsity in gradients and sparsity in weights, etc., and temporal pruning, spatial pruning, you really cannot you cannot really have a lot of efficiency. But our motivation was very much directed towards energy efficiency during inference. After you have come up with this federated framework, and then you're doing on-device inference across these different models, will it show efficiency? And we found out, yes, it does. I showed you some analytical estimations where it was 5x more efficient. So it was completely motivated from inference efficiency.
Okay, great. And I have one last question for you. So you talked about the robustness of these approaches. I think, and I could have missed it, I think it was specifically in the context of to device noise and issues that might occur on chip. Have you also considered looking at it in terms of like adversarial attacks on the input or sensor issues?
Yeah. So yes, the device noise I showed you towards the end, right? Very quickly, I showed you. But there was this slide when I talked about that with BNTT. we find that already, like, SNNs are more efficient, more adversarially resilient, and we found that with BNTT trained models, the adversarial resilience was even better. So yes, we do have, when I talk about robustness, we not only look at noisy inputs or noise statistics coming from the hardware, but also the noise statistics coming from these adversarial attacks. And we found that SNNs are more robust. And if you have proper temporal statistics leveraged inside your training rule, that will give more robustness to the finally trained model, which is what we showed with the BNTT result also.
Fantastic. Thank you so much, Priya. I think we are moving on to the next session now. There's a few more questions here, but thank you so much for your amazing talk, and we'll see you in the next session, everybody. Thanks.
Thank you.